They surfaced at 2200 hours on the night of March 12, 1943, exactly as they had done hundreds of times before. Kapitänleutnant Hans-Joachim Hesse ordered the diesels started, and U-632 rose from the black Atlantic depths into air that smelled of salt and diesel exhaust. The watch crew climbed through the conning tower hatch, their eyes adjusting to darkness broken only by stars. The Metox receiver, mounted in the conning tower, remained silent. No radar signals. No aircraft. They were alone in the mid-Atlantic, 300 miles west of the Bay of Biscay. The chief engineer reported batteries at 42%. They needed 6 hours of surface running to fully recharge, 6 hours of vulnerability, but the Metox would warn them if British aircraft approached. The device had saved them twice already on this patrol, detecting the 1.5-meter wavelength radar emissions from distant aircraft long before those aircraft could detect the U-boat. When Metox's warning light flashed, they had time to dive, to disappear beneath the waves before the enemy could reach them. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Hesse ordered the watch to maintain vigilance while the diesels rumbled, charging batteries and circulating fresh air through compartments that had reeked of unwashed men, diesel oil, and the chemical smell of the carbon dioxide scrubbers. The North Atlantic in March was brutal. Waves crashed over the bow. Spray soaked the watch crew despite their waterproof gear. But this was routine. This was what U-boat crews did every night they could. Surface running was faster, more efficient, and, with Metox providing early warning, it was safe enough. At 23:45 hours, without warning, without any alarm from the Metox receiver, an aircraft roared out of the darkness at masthead height. The first indication was the engine sound, suddenly loud, suddenly close. Then searchlights blazed, turning night into day, illuminating U-632 like an insect pinned to a board. The watch crew saw a twin-engine aircraft, later identified as a Wellington bomber, already committed to its attack run. Hesse screamed for crash dive. The alarm klaxon sounded. Men scrambled through hatches. The Wellington's depth charges fell away. 4 explosions bracketed the U-boat as it slid beneath the surface, close enough that the pressure waves slammed men against bulkheads. Lights flickered. Cork insulation rained from overhead. The stern planes jammed. For 3 minutes that felt like hours, U-632 hung at 60 meters, stern down at a 15-degree angle, while the crew fought to regain control. They survived. The damage was manageable. But as Hesse gathered his officers in the cramped wardroom after they had limped away from the attack site, the question consumed them all. How? The Metox had detected nothing. No radar warning. No indication that any aircraft was within 50 miles. Yet the Wellington had found them in complete darkness, had approached undetected, and had very nearly killed them all. This was not supposed to be possible. The British radar operated at 1.5 meters wavelength. The Metox detected that wavelength reliably at ranges up to 30 kilometers. The mathematics were simple, the physics well understood. If British aircraft were using radar to find U-boats, Metox would provide warning. But Metox had been silent, completely silent. Right up until the searchlights blazed, something had changed. The rules that had governed the Battle of the Atlantic, the tactical calculations that determined when it was safe to surface, when it was necessary to dive, all of it was suddenly uncertain. Somewhere, somehow, the British had developed something new, and U-boat commanders across the Atlantic were about to discover that the ocean had become far more dangerous than any of them had imagined. The confidence that Kapitänleutnant Hesse and thousands of other U-boat commanders felt about night surface operations was not arrogance. It was the product of hard-won experience, careful calculation, and technological advantage that German naval engineers had provided. To understand what made that night in March 1943 so terrifying, you must first understand what U-boat warfare had been, and why the surface had seemed safe. The Type 7 U-boat, which comprised the majority of Germany's submarine fleet, was not truly a submarine in the modern sense. It was a submersible torpedo boat, a vessel designed to operate primarily on the surface with the ability to dive when threatened. The designation reflected this reality. German crews called them Unterseeboot, undersea boats, but they spent most of their operational time on top of the sea, not beneath it. The reasons were fundamental to the technology of the era. Submerged, a Type 7 could manage perhaps 7 knots for 1 hour before its batteries exhausted. Surface running on diesel engines, the same boat could sustain 17 knots for extended periods, limited only by fuel capacity. The tactical implications were stark. A U-boat that remained submerged was slow, blind, and quickly exhausted. A U-boat operating on the surface was fast, could see its surroundings, and could chase down merchant convoys. Battery capacity dictated everything. The Type 7 carried 2 massive banks of lead-acid batteries, 124 cells total, weighing over 60 tons. These batteries powered the electric motors when submerged, but they discharged rapidly under any significant load. At maximum submerged speed, the batteries lasted perhaps 1 hour. At economical submerged speed of 4 knots, perhaps 2 days, assuming perfect conditions and no combat maneuvering. Recharging those batteries required surface running. The diesel engines, 2 supercharged 6-cylinder units producing 3,200 horsepower combined, drove generators that fed current back into the battery banks. A full recharge from 40% capacity took 6 to 8 hours of surface running. During combat patrols in the Atlantic, U-boats typically surfaced every night to recharge, to run their diesels, to ventilate the boat, and to make high-speed transits toward patrol areas or intercept positions. This pattern of operations, surface by night and submerged by day, had evolved from harsh experience in the First World War and the opening years of the current conflict. Early in the war, some U-boat commanders attempted to operate submerged during daylight hours when aircraft could spot them easily. But sustained submerged operations meant slow movement, rapid battery depletion, and reduced effectiveness. Boats that stayed down too long became sitting targets when they finally had to surface with depleted batteries. By 1941, U-boat tactics had evolved into a refined system. Surface at night when visibility was poor and aircraft blind. Run the diesels to charge batteries and make transit. Submerge before dawn when aircraft became a threat. Remain submerged during daylight, conserving battery power, maneuvering slowly to remain on patrol station. Surface again at dusk, and repeat the cycle. It was a rhythm as regular as breathing, and it worked. The introduction of British air patrols over the Atlantic in 1940 and 1941 complicated this pattern. Aircraft equipped with radar could detect surfaced U-boats even at night, even in poor visibility. But German naval intelligence identified the threat, and German engineers provided a solution. The Metox receiver, officially designated FU-MB-1, entered service in mid-1942. Metox was elegantly simple. It detected the radar emissions from British aircraft at ranges significantly greater than the Prophet. Radar itself could detect the U-boat. British ASV Mark II radar, the standard equipment on coastal command aircraft, operated at 1.5 meters wavelength. It could detect a surfaced U-boat at perhaps 5 to 8 miles under good conditions. The Metox receiver could detect that radar's emissions at 18 to 20 miles. The mathematics created a safety margin. If a U-boat surfaced with Metox operating, the crew would receive warning of approaching aircraft long before that aircraft's radar could detect them. Warning time varied based on conditions, but typically allowed 3 to 5 minutes to dive to safety. For U-boat commanders, this meant night surface operations remained viable despite British radar-equipped aircraft. The device itself was crude but functional. A wooden cross-shaped antenna array, nicknamed the Biscay Cross for its resemblance to a crucifix, and its use in the dangerous waters of the Bay of Biscay. Technicians mounted it in the conning tower, where it rotated to detect radar signals from any direction. The receiver unit occupied space inside the boat, connected by cable to the antenna. When it detected radar emissions at 1.5 meters wavelength, a warning light illuminated and a tone sounded in the control room. Metox transformed U-boat tactics. Commanders who had been forced to remain submerged at night or surface only in the worst weather when aircraft could not fly, could now surface with confidence. The warning system worked. Boats equipped with Metox received timely warnings, dove before aircraft arrived, and survived. Boats without Metox were caught on the surface and attacked. The statistical evidence was overwhelming. Metox saved lives and boats. By early 1943, virtually every operational U-boat carried Metox equipment. Commanders trusted it absolutely. The device had proven itself in combat. It detected British radar reliably. It provided adequate warning time. When the Metox was silent, the sky was clear. When it sounded, danger approached, and you dove. Simple, reliable, proven. This trust, built on months of successful operations and verified saves, made what happened to U-632 and dozens of other boats in March and April of 1943 completely incomprehensible. The confidence U-boat commanders felt extended beyond simple trust in their detection equipment. It rested on a broader understanding of their enemy's capabilities, an understanding built from intelligence reports, captured equipment, and the observed patterns of British operations. German naval staff knew what radar the British used because they had studied it carefully. That knowledge made the impossible attacks of spring 1943 even more disturbing. British radar technology was no mystery to German intelligence. In February 1943, German forces had recovered nearly intact ASV Mark II radar equipment from a crashed Wellington bomber near Rotterdam. Technicians at Telefunken examined every component. They measured the wavelength at precisely 1.5 meters. They tested the transmitter power output. They calculated detection ranges based on the antenna design and power levels. Everything matched what Metox had been designed to detect. This captured equipment confirmed what German engineers already believed. British airborne radar operated at 1.5 meters. This wavelength was well suited for detecting large metal objects like ships or surfaced submarines, and the British had built an entire operational system around it. Coastal Command had equipped hundreds of aircraft with ASV Mark II. Metox detected ASV Mark II. Therefore, Metox protected U-boats from radar-equipped aircraft. The logic was sound, the evidence clear, the conclusion inescapable. What German intelligence did not know, could not know from examining crashed aircraft and intercepted signals, was that British scientists had already moved beyond the 1.5-meter radar that Germany understood so well. The revolution had occurred quietly, in university laboratories and secret research facilities, years before German intelligence recognized anything had changed. The breakthrough came in February 1940 at the University of Birmingham. Two physicists, John Randall and Harry Boot, working under Professor Mark Oliphant, developed a device called the cavity magnetron. This was not an incremental improvement in existing radar technology. It was a fundamental leap that changed what was possible. The cavity magnetron could generate microwave radiation at 10 centimeters wavelength, with power levels previously unimaginable at such high frequencies. Before the cavity magnetron, radar systems were large, heavy, and relatively low-powered at shorter wavelengths. The 1.5-meter systems that equipped British aircraft were about as good as the technology could achieve while remaining practical for installation in aircraft. Shorter wavelengths would provide better resolution and more focused beams, but generating sufficient power at shorter wavelengths required equipment too large and heavy for aircraft use. The cavity magnetron solved this problem completely. It was compact, about the size of a large fist. It was powerful, generating kilowatts of microwave energy, and it operated at 10 centimeters, a wavelength that allowed for much smaller antennas and tighter beam focus than the 1.5-meter systems. This meant an aircraft could carry a radar set that was both more powerful and more compact than previous designs. British scientists and engineers recognized immediately what they had created. This was not just an improvement in existing radar. This was enabling technology for an entirely new generation of radar systems. By mid-1940, even as the Battle of Britain raged, scientists at the Telecommunications Research Establishment were already designing airborne radar systems around the cavity, magnetron. The British government made a fateful decision. In August 1940, as Britain stood alone against Germany, a technical mission travelled to the United States, carrying Britain's most closely guarded technological secrets. The mission, led by Sir Henry Tizard, included samples of the cavity magnetron. American scientists who saw the device recognized its significance immediately. One American scientist reportedly said it was the most valuable cargo ever brought to American shores. The Americans committed their vast industrial capacity to mass-producing cavity magnetrons and the radar systems built around them. By 1942, production lines in the United States were manufacturing thousands of 10-centimeter radar units monthly. Some went to American forces. Many went to Britain under Lend-Lease agreements. And throughout 1942, while U-boat commanders surfaced confidently each night with Metox providing reassuring silence, British engineers were fitting aircraft with a radar system that Metox could not detect. The new system, designated ASV Mark III, began entering service with RAF Coastal Command in late 1942. The first equipped squadrons flew patrols in February 1943. The equipment worked exactly as designed. Detection ranges against surfaced U-boats reached 12 to 15 miles under good conditions, sometimes more. The 10-centimeter wavelength was completely invisible to Metox receivers designed to detect 1.5-meter emissions. From the British perspective, this was a hunting revolution. Aircraft equipped with ASV Mark III could find U-boats that had no warning of their approach. U-boat commanders who trusted Metox to warn them of danger surfaced confidently, ran their diesels, charged their batteries, and never knew they were being tracked until searchlights blazed and depth charges fell. The statistics changed almost immediately. In March 1943, Coastal Command, aircraft sank 7 U-boats and damaged many more. In April, the numbers climbed to 8, sunk with numerous damaged boats limping home. In May, traditionally the peak month of the convoy battles, the slaughter intensified. 15 U-boats were sunk by aircraft in the Bay of Biscay alone, most of them caught on the surface without warning. But from the German perspective, what was happening made no sense at all. U-boats were being attacked at night with no radar warning. Metox remained silent. No radar emissions detected. Yet aircraft appeared out of darkness with perfect intercepts. Some commanders reported being attacked in total darkness before searchlights illuminated. Others reported Metox silence right up until bombs fell. The pattern was consistent and terrifying. The British had something new, something Metox could not detect, and U-boat crews were dying without understanding what hunted them. Korvettenkapitän Peter Dönitz, son of Admiral Karl Dönitz, who commanded all U-boat operations, was among those who surfaced confidently in May 1943. His boat, Union 54, ran on the surface in the Bay of Biscay on the night of May 19th. Metox was silent. The sea was empty. At 23:15 hours, a Sunderland flying boat attacked without warning. Union 54 managed to dive, but depth charges damaged the pressure hull. The boat was forced to surface. Aircraft attacked again. The crew abandoned ship. Peter Dönitz died in the water from his injuries. His father, the Admiral, received notification 3 days later. This was personal now. It was also strategic catastrophe. The entire U-boat operational system depended on surface running to recharge batteries and make transit. If the surface was no longer safe, if Metox no longer provided adequate warning, then the fundamental tactics that had sustained the U-boat campaign for years were obsolete. But what had changed? What were the British using? And how could U-boats survive if they could not trust their warning systems? These questions consumed German naval staff and U-boat commanders throughout that terrible spring of 1943, as the Battle of the Atlantic turned decisively against them, and no one could explain why. The theories began circulating through the U-boat fleet almost immediately, in the cramped wardrooms of submarines returning from patrol, in the concrete bunkers that housed U-boat crews at Lorient and Saint-Nazaire, in the staff offices at WWII headquarters, where Admiral Dönitz and his operations officers plotted the Atlantic campaign, men grasped for explanations that made sense. Each theory reflected what they knew, what they feared, and what they could not yet imagine. The most persistent theory blamed the Metox itself. Some commanders reported that British aircraft seemed to home in on their positions specifically when Metox was operating. Perhaps, they suggested, the Metox receiver itself emitted radiation that British aircraft could detect. The receiver's local oscillator, necessary for detecting incoming signals, did produce low-level emissions. Perhaps British scientists had developed equipment sensitive enough to detect these emissions and use them as a homing beacon. German electronic warfare specialists investigated this theory extensively. They tested Metox receivers in laboratories, measuring emissions at various ranges. The results were ambiguous. Yes, Metox produced detectable emissions, but at power levels so low that detecting them at operational ranges seemed impossible with any plausible technology. Nevertheless, Admiral Dönitz ordered all boats to use Metox sparingly, operating it only for brief periods, rather than continuously. The attacks continued. Boats that barely used Metox were caught just as easily as those that operated it constantly. Another theory proposed that British aircraft had developed infrared detection equipment that could locate U-boats by the heat signature of their diesel engines. U-boat diesels running at full power to charge batteries produced significant heat. Exhaust gases vented through ports in the conning tower. Perhaps, some argued, British scientists had built infrared cameras sensitive enough to detect this heat from miles away in total darkness. This theory had superficial plausibility. Infrared technology existed. The Germans themselves had experimented with it, but the ranges required seemed impossible. Infrared radiation dissipates quickly through atmosphere and is strongly affected by water vapor, which the Atlantic provided in abundance. Detecting a heat source at 10 or 15 miles through maritime atmosphere at night seemed beyond any technology anyone understood. Still, lacking better explanations, some commanders began dousing their engine rooms with seawater to reduce heat signatures when surfacing. The attacks continued. A darker theory blamed treachery. Perhaps, some suggested, the British had broken German naval codes and were reading U-boat position reports. Perhaps they were tracking U-boats through radio direction, finding with equipment far more sophisticated than Germany possessed. Perhaps Allied agents had infiltrated U-boat bases and were reporting departure times and patrol areas. This theory reflected growing paranoia as losses mounted and explanations remained elusive. German naval intelligence investigated code security exhaustively. The Enigma cipher machines that encrypted all U-boat communications were considered unbreakable. Mathematically, the number of possible settings was astronomical. Even if the British captured a machine, which they had, they could not break the daily key settings quickly enough to make tactical use of intercepted messages. That was the assessment. That was the assumption. It was wrong, but German cryptographers would not discover this until after the war ended. The investigations, the theories, the desperate attempts to understand what was happening consumed resources and attention while providing no useful answers. U-boat crews went to sea knowing they were being hunted by something they could not detect, could not understand, and could not effectively counter. The psychological impact was devastating. Trust in equipment eroded. Confidence in surface operations collapsed. Men who had volunteered for submarine service, who had been among the elite of the German Navy, now went to sea expecting to die. Kapitänleutnant Horst von Schroeter, commanding U-667, wrote in his war diary after a patrol in April 1943 that his crew was exhausted not from combat but from fear. They surfaced only when absolutely necessary for battery charging. They dove at the slightest sound, real or imagined. They spent most of each patrol submerged, moving slowly to conserve batteries, accomplishing nothing. Von Schroeter wrote that he felt hunted by an invisible enemy, using weapons he could not understand. The patrol achieved nothing. They sighted no convoys, attacked no ships, and spent their time hiding underwater. Statistical analysis painted a grim picture. In March 1943, U-boats sank 63 merchant ships in the Atlantic, but 15 U-boats were lost. In April, 39 merchant ships sunk, 15 U-boats lost. In May, traditionally the peak of convoy battles when extended daylight allowed sustained attacks, only 50 merchant ships were sunk, while 41 U-boats were destroyed. The exchange rate had turned catastrophically against Germany. Admiral Dönitz, reviewing these figures in his headquarters, recognized what was happening even if he could not explain it. The British had achieved some technological breakthrough that fundamentally altered the tactical balance. Whatever it was, it had neutralized the U-boat's ability to operate on the surface with any degree of safety. On May 24, 1943, Dönitz made a decision that acknowledged defeat in the Atlantic campaign without calling it that. He ordered all U-boats to withdraw from the North Atlantic convoy routes. The order stunned U-boat commanders. For 3 years, the Atlantic had been their primary hunting ground. The convoy routes between Britain and North America were where the war would be won or lost. If U-boats could not operate there, if they abandoned that battlefield, then what was the purpose of the U-boat fleet? But Dönitz had no choice. Losses were unsustainable. Until German scientists could identify what the British were using and develop countermeasures, sending U-boats into the North Atlantic was sending men to die for no strategic gain. The withdrawal order came with instructions to maintain aggressive patrols in areas where air cover was less intensive: the Central Atlantic, the Caribbean, the South Atlantic off Africa. But these were secondary theatres with fewer targets and less strategic impact. The Battle of the Atlantic, the struggle to strangle Britain's supply lines, was effectively over. Not because U-boats lacked courage or skill, but because they lacked understanding of what hunted them. In the weeks following the withdrawal, German scientists and engineers worked frantically to develop new detection equipment. If British aircraft were using some new form of radar at wavelengths Metox could not detect, then Germany needed receivers that covered broader frequency ranges. The Naxos radar detector, covering frequencies from 8 centimeters to 12 centimeters, entered development. But development takes time. Testing takes time. Production and deployment take more time. U-boats needed protection now, and Germany could not provide it. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Meanwhile, in Britain, the secret of what had turned the Battle of the Atlantic remained closely guarded. RAF Coastal Command crews knew they had new radar that the enemy could not detect. They knew it worked brilliantly, but they did not discuss it outside secure facilities. They did not write about it in letters home. Security was absolute because the advantage was total. As long as the Germans did not know about 10-centimeter radar, as long as they could not develop countermeasures, British aircraft could hunt U-boats with impunity. Flight Lieutenant Wilfred Oulton banked his Vickers Wellington bomber into a gentle turn, maintaining altitude at 2,000 feet over the Bay of Biscay. The night of June 5, 1943, was clear with good visibility once your eyes adjusted to darkness. Below, somewhere in that vast darkness, U-boats were transiting. They had to be. The Bay of Biscay was a choke point, the only route for U-boats based in French ports to reach the Atlantic hunting grounds. Alton's Wellington, serial number HF 230, from number 172 Squadron, based at Chivanor, carried the ASV Mark III radar that had been installed just 3 weeks earlier. The squadron had trained intensively on the new equipment. The radar operator, Sergeant James Mackenzie, sat at his scope in the fuselage, watching the cathode ray tube display for the distinctive echo that would indicate a surfaced submarine. The old ASV Mark II had shown contacts as bright blips on a circular scope, but range estimation was difficult, and ground returns cluttered the display near coastlines. The Mark III was different. The scope showed range clearly on one axis and bearing on the other. The antenna, mounted in a radome beneath the aircraft's belly, rotated continuously, painting a picture of everything below, and the resolution was remarkable. A surfaced U-boat showed as a clear, distinct contact at ranges the old equipment could never have achieved. At 01:15 hours, Mackenzie's voice crackled through the intercom. Contact. Bearing 270, range 13 miles. Toward the indicated bearing, while Navigator Flying Officer Dennis Carter began plotting the intercept, 13 miles. At the Wellington's cruising speed of 160 miles per hour, they would reach the contact in approximately 5 minutes. Mackenzie watched the scope, calling out range updates. 12 miles. 11 miles. The contact remained steady, not moving, likely a U-boat recharging batteries. At 8 miles, Alton began descending to attack altitude, maintaining speed. At 4 miles, he ordered the ley light prepared. This was the combination that had proven devastatingly effective. ASV Mark III detected the U-boat at ranges where the submarine's lookouts had no chance of spotting the aircraft. The Wellington could approach completely undetected, throttling back for the final run to reduce engine noise. Then, at the last moment, the ley light would blaze, illuminating the submarine in a pool of brilliant white light that destroyed the night vision of the U-boat's watch crew and gave the aircraft perfect visual reference for its attack run. The ley light was a 22 million candle power searchlight mounted in the Wellington's retractable ventral turret position. Squadron leader Humphrey Lee had developed the concept in 1941, but the light only became truly effective when paired with radar that allowed precise navigation to the target. With ASV Mark II, aircraft often lost contact in the final miles of approach and had to search visually, alerting the U-boat. With ASV Mark III, the Wellington could navigate precisely to within a quarter mile before switching on the light. At 1 mile, Mackenzie called final range. Alton throttled back slightly, descending to 150 feet. The Wellington's bomb aimer, Sergeant Ronald Fletcher, lay prone in the nose position, ready to sight and release. At a quarter mile, Alton gave the order. The lee light snapped on, and night became day. Below, U-417 had been surfacing for 38 minutes, running diesels at full power to charge batteries depleted by 2 days submerged. The watch crew scanned the darkness, looking for aircraft, listening for engine sounds. They saw nothing, heard nothing except their own diesels. The Metox receiver in the conning tower was silent. Then the light hit them. Oberleutnant Zur. C. Wolfgang Schreiner, commanding U-417, was in the conning tower when the night exploded into brilliance. His first thought was illumination flares, but this was wrong. This was a searchlight, impossibly bright, turning the submarine and surrounding ocean into a daylight scene. His second thought was crash dive, but it was already too late. The Wellington was overhead, the bomb aimer releasing 4 depth charges that fell away in a perfect stick. Schreiner was screaming dive orders as the first depth charge detonated 15 meters from U-417's starboard beam. The explosion lifted the submarine bodily, throwing men against steel. The conning tower watch crew, blinded by the searchlight, never made it below. Schreiner fell through the hatch as the submarine's bow dipped. The second depth charge exploded directly over the pressure hull aft of the conning tower. Atlantic Ocean, at 100 meters depth, exerts pressure of 10 atmospheres, 147 pounds per square inch. When the hull cracked, that pressure differential drove a jet of water into the control room with the force of a high-pressure cutting tool. The jet struck the electrical panels, shorting out systems. The lights failed. Emergency lighting provided only dim red illumination as water sprayed into darkness. The third and fourth depth charges detonated as U-417 passed through 30 meters depth, no longer diving under control but sinking. The explosions destroyed the stern planes and ruptured tanks. The submarine continued sinking stern first. At 60 meters, Schreiner ordered blow all tanks, using precious high-pressure air to force water from ballast tanks and arrest the descent. It worked. U-417 hung at 65 meters, barely under control, taking water through the cracked hull section. Damage reports came through the speaking tubes. The electric motors were flooded and inoperative. The stern torpedo room was taking water. The rudder was jammed. Schreiner assessed their situation in the darkness of the control room. They could not remain submerged with water coming in. They could not maneuver. The diesels were undamaged, but running diesels submerged would poison the crew with carbon monoxide within minutes. They had to surface, attempt repairs, and hope the aircraft had left. U-417 surfaced at 01:40 hours, 23 minutes after the attack. The crew flooded onto the deck, some manning the 88mm deck gun, others working on damage control. Schreiner expected the aircraft to return. It did. Alton had orbited the attack site, maintaining radar contact with the damaged submarine. When U-417 surfaced, the Wellington was already positioned for a second attack run. This time the U-boat fought back. The deck gun crew got off 3 rounds at the approaching aircraft, the muzzle flashes bright in darkness. None found their target. The Wellington came in lower, its front gunner firing the nose-mounted Browning machine guns, tracer rounds walking across the submarine's deck. Men dove for cover. The bomb aimer released 4 more depth charges. These exploded alongside the wallowing submarine, and that was enough. The pressure hull, already cracked, split open completely. U-417 began sinking immediately, bow rising, stern disappearing beneath the waves. Men scrambled to launch the rubber dinghies stored in deck containers. Some succeeded, some did not. Schreiner was last off the submarine, tradition demanding it. He stepped into the Atlantic as his boat disappeared. Of 48 crew, 23 survived to be picked up by a British destroyer 18 hours later. Oberleutnant Schreiner, wrapped in blankets aboard HMS Wanderer after his rescue, struggled to comprehend what had happened. The British destroyer's captain, Commander Roderick H.D. Bauer, allowed him to warm up and receive medical attention before interrogation began. When it did, Schreiner's first questions were not about his fate, but about how the aircraft had found him. Commander Bauer said nothing, but the interrogating naval intelligence officer, careful to reveal nothing classified, simply noted Schreiner's questions in his report. German prisoners consistently asked the same things. How did the aircraft find us? What kind of radar are you using? Why didn't our Metox provide warning? The intelligence officer gave standard non-answers. Operational security prevented discussing British capabilities. But internally, Allied intelligence found these questions fascinating because they revealed how completely the Germans misunderstood what they faced. The interrogation reports from U-417's survivors and dozens of other captured U-boat crews that summer of 1943 showed a consistent pattern. German submariners believed they were facing some exotic technology, something beyond normal radar. They theorized about infrared detectors, about ultra-sensitive direction-finding equipment, about radiation detection devices that could sense their Metox receivers. Some believed the British had deployed acoustic sensors that could hear diesel engines from dozens of miles away. None of them guessed the truth because the truth was simpler than any exotic theory. The British were using radar. Just radar. But radar at a wavelength German equipment could not detect. Operating at ranges German engineers had not believed possible for airborne systems and produced in quantities that allowed equipping hundreds of aircraft. The technological leap was significant, but it was not mysterious physics. It was engineering, production capacity, and operational security. By June 1943, RAF Coastal Command had equipped nearly 300 aircraft with ASV Mark III. Wellingtons, Sunderlands, Liberators, and Halifaxes all carried the 10-centimetre radar. The maintenance requirements were substantial. The cavity magnetrons had limited operational life and needed frequent replacement. The radar sets required constant calibration. But British and American production was delivering magnetrons by the thousands, and trained technicians kept the equipment operational. The operational impact was measurable in ways that left no doubt about what was happening. In the 3 months before ASV Mark III entered widespread service, from November 1942 through January 1943, Coastal Command aircraft sank 14 U-boats. In the 3 months after widespread deployment, from March through May 1943, aircraft sank 43 U-boats. The increase was nearly threefold, and the pattern was unmistakable. German naval staff could see the statistics. They knew aircraft losses had increased dramatically. What they could not determine was why. Admiral Dönitz authorized technical intelligence operations to capture or recover British radar equipment. On June 2, 1943, German forces in the Netherlands recovered wreckage from a crashed Sterling bomber that had been equipped with H-2S ground mapping radar, another 10-centimetre system. Technicians examined the equipment and confirmed what they had feared. The British had operational centimetric radar. But knowing the wavelength did not immediately provide solutions. Germany's electronics industry, already strained by war production demands, needed time to develop detection equipment covering the centimetric bands. The Naxos receiver, designed to detect 10-centimetre radar, would not enter production until early 1944. The Mucker receiver, covering even broader frequency ranges, came later still. For U-boats at sea in summer and fall of 1943, there was no technical solution, only tactical adaptation. The tactical changes Admiral Dönitz ordered reflected the grim reality that U-boats could no longer operate safely on the surface within range of Allied aircraft. U-boats were instructed to remain submerged during daylight hours, regardless of battery state. Surface running was restricted to nighttime hours in areas where air patrols were least intensive. Transit through the Bay of Biscay, previously conducted on the surface at high speed, now required submerged transit, which quadrupled transit time and exhausted batteries. These changes reduced U-boat effectiveness dramatically. A Type 7 U-boat that previously could transit from French bases to mid-Atlantic patrol areas in 5 days now required 3 weeks. Most of it spent submerged, moving slowly, conserving batteries. Once on station, the submarine spent most of its time submerged, unable to chase convoys or maneuver for attack positions. Battery limitations meant reduced patrol duration. Boats that previously stayed on station for 4 weeks now returned after 2 weeks with depleted batteries and limited accomplishments. The kill-to-loss ratio told the story in stark numerical terms. In 1942, before ASV Mark III deployment, U-boats sank approximately 6.3 merchant ships for every U-boat lost. In the second half of 1943, after centimetric radar became widespread, the ratio collapsed to less than 1 merchant ship sunk per U-boat lost. The campaign was not sustainable. Germany was losing submarines faster than shipyards could replace them, and each lost boat took trained crews that could not be quickly replaced. Individual U-boats experienced the change as a shift from hunting to survival. Kapitänleutnant Herbert Werner, who survived the war and later wrote a memoir, described patrols in late 1943 as exercises in futility. His boat, U-230, spent a 6-week patrol, accomplishing almost nothing. They sighted one convoy but could not reach attack position while submerged. They surfaced twice for battery charging and were forced to crash dive both times by aircraft they never saw until searchlights blazed. They returned to base having sunk no ships, having barely survived. The psychological toll on U-boat crews became severe. Men volunteered for submarine service knowing it was dangerous, but expecting they had reasonable chances of survival if they were skilled, careful, and lucky. By late 1943, skill and care seemed irrelevant. Aircraft appeared without warning. You surfaced to charge batteries because you had no choice, and you waited to see if tonight would be the night a searchlight found you. Some crews developed superstitions, believing certain boats were lucky, certain commanders were safe. None of it made any difference. The German Navy's medical service reported increasing cases of psychological breakdown among U-boat crews. Men who had completed multiple patrols successfully requested transfer to surface ships, accepting the disgrace rather than return to submarine duty. Combat effectiveness, degraded as exhausted, frightened crews made mistakes that peacetime training had eliminated. Morale collapsed. The elite service that had attracted Germany's best sailors now struggled to find volunteers willing to face nearly certain death. Admiral Karl Dönitz faced a strategic problem with no good solution. By autumn of 1943, the Battle of the Atlantic was effectively lost, though the fighting would continue for another 18 months. U-boats still went to sea, crews still hunted convoys. But the fundamental equation had changed. The submarines could no longer operate with the freedom of movement necessary for effective commerce raiding, and no amount of tactical innovation could restore what centimetric radar had taken away. The German response, when it finally came, addressed symptoms rather than causes. In September 1943, U-boats began receiving upgraded anti-aircraft armament. The standard 20mm gun was replaced with quad-mounted 20mm guns and a 37mm automatic cannon. The theory was straightforward. If U-boats could no longer dive quickly enough to escape attacking aircraft, they would fight on the surface. Crews received orders to remain surfaced when attacked and shoot it out with the aircraft. This tactical change reflected desperation rather than analysis. A surfaced U-boat, even heavily armed, was a poor match for a 4-engine bomber carrying depth charges and equipped with front-firing machine guns. The aircraft could attack from any angle, could break off and circle for another run, and could call for additional aircraft if the first attack failed. The U-boat was stationary or slow-moving, constrained to its deck gun positions, unable to maneuver effectively. U-boats that chose to fight on the surface sometimes drove off individual aircraft, but they suffered casualties among deck gun crews and often sustained damage that forced them to abort patrols. Some boats were destroyed in these surface battles. Others were damaged badly enough that aircraft could track them until surface warships arrived to finish the kill. The policy killed men and submarines while accomplishing nothing strategically. Kapitänleutnant Klaus Bargston, commanding U-521, attempted to fight it out with an attacking Sunderland flying boat in the Bay of Biscay on September 17, 1943. His anti-aircraft guns damaged the Sunderland, but the flying boat's depth charges straddled U-521, causing severe damage. Bargston managed to dive, but the boat could only reach 40 meters before water flooding through sprung plates forced him to surface. A second aircraft attacked. This time Bargston surrendered rather than sacrifice more crew. Of his complement of 52 men, 14 were already dead or dying from the first attack. The technological race continued, but Germany was always behind. When Naxos radar detectors finally reached U-boats in early 1944, they could detect 10-centimeter radar, but Allied forces were already deploying 3-centimeter radar in some aircraft. The Naxos helped, providing some warning, but it was not the complete solution. Metox had been against 1.5-meter radar. Detection ranges were shorter. False alarms from Allied surface ships' radar were common, and by this point, Allied air superiority was so complete that detecting radar often meant only that you knew why you were about to die. German engineers proposed technological solutions that might have restored some balance. The Schnorkel, a breathing tube that allowed submarines to run diesels while submerged at periscope depth, entered service in mid-1944. This reduced vulnerability to radar detection by keeping the hull underwater, but it introduced new problems. Speed while snorkeling was limited to 6 or 7 knots. The Schnorkel itself could be detected by radar under calm sea conditions, and operating with the Schnorkel was miserable for crews, as exhaust gases often leaked into the boat, and the diesel engines could suck air from the pressure hull faster than the Schnorkel could supply it, creating painful pressure changes. The Type XXI U-boat, designed as a true submarine rather than a submersible, promised revolutionary capability. With massive battery capacity, streamlined hull design, and underwater speed of 17 knots, the Type XXI could have changed the dynamics of submarine warfare. But the first operational boat did not go to sea until April 1945, weeks before Germany's surrender. Only 2 Type XXI submarines completed combat patrols, and neither engaged Allied shipping. The technology arrived too late to matter. Meanwhile, the actual combat continued its grim trajectory. U-boats still sailed, still hunted, still occasionally sank merchant ships, but the losses were unsustainable. In 1944, Germany lost 242 U-boats. In the first 4 months of 1945, another 153 were destroyed. Coastal Command aircraft accounted for a large percentage of these kills, most of them detected by ASV Mark III radar long before the U-boats knew danger approached. The mathematics of submarine warfare had turned completely against Germany. Building a U-boat required approximately 300,000 man-hours of labor and scarce materials, including steel, copper, and rubber. Training a crew required 6 months. The investment was substantial. Allied forces were destroying these boats faster than German. Industry could replace them, and doing so at relatively low cost. A coastal command aircraft represented less investment than a U-boat, could fly multiple patrols daily, and could be replaced more quickly if lost. Some U-boat commanders, recognizing the futility, began surfacing and surrendering when attacked rather than fighting or diving. Others refused to surface at all when ordered on patrol, claiming mechanical problems that required return to base. A few boats simply disappeared, possibly scuttled by their own crews who preferred internment in neutral countries to death in the Atlantic. These were not cowards. These were men who understood that continuing the fight meant certain death with no reasonable chance of accomplishing anything meaningful. The crews who continued fighting, who took their boats to sea knowing the odds, deserve recognition for courage even in a losing cause. But courage without adequate equipment and realistic tactics is simply sacrifice, and Germany was, sacrificing its submarines and submariners for diminishing returns. Every U-boat that sailed after mid-1943 was fighting not to win, but simply because orders demanded it, and honor required continuing until the end. By early 1945, U-boats in port often lacked fuel for patrols. Allied bombing had destroyed synthetic fuel plants. What fuel remained was allocated to aircraft and tanks for the defense of Germany itself. Some submarines never left port in the final months. Their crews formed into infantry units to fight in the collapsing defensive lines. The U-boat force that had nearly strangled Britain in 1942 ended the war largely immobilized, out of fuel, out of luck, and out of time. On the night of March 12, 1943, when Kapitänleutnant Hans-Joachim Hesse's U-632 surfaced in the mid-Atlantic and was attacked without warning. He experienced a moment that would be repeated hundreds of times in the following months. The moment when confidence based on experience and trust in equipment collides with a reality that renders both obsolete. It was the moment when the Battle of the Atlantic turned decisively, though no one could see it clearly at the time. Hesse survived that night. U-632 limped back to Saint-Nazaire with significant damage. Hesse reported the attack in detail, describing how Metox had provided no warning, how the aircraft had appeared suddenly, how the submarine had barely escaped. His report joined dozens of others describing similar attacks. German naval intelligence compiled these reports, analyzed them, sought patterns and explanations. But understanding came slowly, too slowly to save the men still going to sea in boats that could no longer protect them. The human cost of this technological gap extended beyond the 28,000 German submariners who died. Merchant seamen continued dying on torpedoed cargo ships even as U-boat effectiveness declined. Allied sailors on escort ships died fighting submarines. Coastal Command aircrews died when their aircraft were shot down by U-boats fighting on the surface or when mechanical failures sent them into the ocean. The Battle of the Atlantic was not a clean technological competition. It was industrial warfare at its most brutal, where innovation measured its success in enemy casualties and its own losses. But the technological dimension mattered because it determined the tactical possibilities available to both sides. When U-boats could surface safely at night, they could chase convoys, position for attacks, and operate effectively. When the surface became a killing zone, when any surfaced submarine risked destruction by aircraft it could not detect, the entire operational system collapsed. No amount of courage or tactical skill could overcome the fundamental vulnerability that centimetric radar created. The irony, apparent with historical perspective, was that the technology was not exotic. 10-centimeter radar was an engineering achievement, certainly, but it was not mysterious physics. It was microwave generation, antenna design, signal processing, all within established scientific understanding. What made it decisive was production scale and operational security. The Allies produced cavity magnetrons by the thousands, equipped hundreds of aircraft, maintained operational security that prevented the Germans from understanding what they faced until too late. Germany's failure was not scientific. German physicists understood microwave radiation. German engineers could have developed centimetric radar given resources and priority. But Germany's industrial base, strained by a multi-front war, could not match Allied production capacity. And German strategic planning, which had prioritized offensive weapons over defensive technologies, left gaps in areas like radar detection that proved fatal. For the individual U-boat crews who sailed into the Atlantic in 1943 and 1944, these strategic considerations were irrelevant. They knew only that they were being hunted by something they could not counter, that their odds of survival diminished with each patrol, and that orders required them to continue anyway. Some men broke under this pressure. Most continued serving, perhaps because military discipline demanded it, perhaps because camaraderie with their crewmates provided meaning, perhaps because accepting death was easier than confronting the alternative. The story of centimetric radar and its impact on the Battle of the Atlantic illustrates a broader truth about technological warfare. The side that innovates first gains advantage, but only if that innovation can be produced at scale, deployed effectively, and protected through operational security. The cavity magnetron succeeded on all three dimensions. British scientists innovated, Allied industry produced, and security services kept the secret long enough to gain decisive advantage. This pattern would repeat throughout the 20th century. Radar itself would evolve through the Cold War, with each advance in detection capability prompting countermeasures and stealth technologies. The fundamental competition between sensors and concealment, between detection and evasion, continues in modern warfare. But the Battle of the Atlantic provided an early, stark example of how technological superiority in a single domain can determine strategic outcomes. For historians examining the Battle of the Atlantic, the deployment of centimetric radar represents a clear turning point. The statistics show it. U-boat effectiveness declined sharply from spring 1943 onward. Losses spiked. The exchange ratio of merchant ships sunk to U-boats lost collapsed. Admiral Dernitz's withdrawal of submarines from the North Atlantic convoy routes in May 1943 acknowledged defeat, even if it was not formally declared as such. But for the men involved, the experience was less about statistics than about the terrible knowledge that they were fighting with inadequate tools. The U-boat crews knew, in those final years of the war, that they were being sent to sea to die. Some accepted this. Others rebelled quietly, claiming mechanical problems, avoiding combat, surrendering when attacked. And some continued fighting effectively, scoring occasional successes, sinking merchant ships, justifying their service through continued resistance, even when strategic victory was impossible. Flight Lieutenant Wilfred Oulton, whose Wellington bomber destroyed U-417 in June 1943, flew 46 operational patrols during the war. He survived, was decorated for his service, and returned to civilian life in Britain. He rarely discussed his wartime service in detail, but in a 1980s interview, he acknowledged that the technology had made the crucial difference. The ASV Mark III allowed him to find submarines that had no chance of detecting him first. It was, he said, almost unsporting, except that war is not sport, and the goal is victory, not fairness. This perhaps captures the essential truth. The technological advantage that centimetric radar provided was absolute within its domain. U-boats could not effectively counter it once deployed. But this advantage existed within a larger context of Allied superiority in production, logistics, and coordination. The radar worked because hundreds of aircraft carried it, because maintenance crews kept it operational, because intelligence guided patrol areas, because the entire system of anti-submarine warfare had matured into an effective, integrated operation. Germany lost the Battle of the Atlantic not because of a single technological failure, but because it was outmatched across every dimension of industrial warfare. But centimetric radar was the cutting edge of that defeat, the specific technology that turned U-boat vulnerability from manageable risk to near certainty. And for the men who died because their Metox receivers could not detect 10-centimeter wavelength emissions, the distinction between single-point failure and systemic defeat was meaningless. They surfaced to charge batteries, as operational necessity required, and died when aircraft they could not sense attacked with weapons they could not avoid. The lesson, if there is one beyond the obvious tragedy, is that in technological warfare, knowing your enemy's capabilities is essential, but not sufficient. You must also anticipate what capabilities they might develop, invest in countermeasures before threats materialize, and maintain the industrial and scientific base to compete across the full spectrum of military technology. Germany failed on all these counts in the radar competition. The cost was measured in submarines lost, crews killed, and a campaign that might have succeeded had the technological balance been different. Kapitänleutnant Hesse, who's confused, the report from March 1943 helped begin the investigation into what was hunting U-boats, survived the war. U-632 was eventually sunk in July 1944 by depth charges from a British frigate, but Hesse was not aboard. He had been reassigned to training command after his boat sustained too much damage to repair quickly. He spent the final year of the war teaching new U-boat crews the tactics that he knew were obsolete, preparing men for service in boats he knew were inadequate, sending them to an Atlantic that he knew had become a graveyard. After the war, Hesse lived quietly in Bavaria, worked in civil engineering, and rarely discussed his service. But in a letter to a fellow U-boat veteran in 1968, he wrote that the worst part of those final years had been the knowledge. Knowing they were defeated, knowing the equipment was inadequate, knowing men were dying for a lost cause, but continuing because that was what duty required. He wrote that learning about the centimetric radar, understanding finally what had hunted them, provided strange relief. At least there had been a reason. At least the defeat had been real, material, based on technology rather than cowardice or incompetence. That need to understand, to assign cause, to find meaning in defeat, runs through the accounts of surviving U-boat veterans. The Battle of the Atlantic cost them comrades, years of their lives, and ultimately the war itself. But knowing that they had been beaten by innovation and production, rather than failing through their own inadequacy, allowed them to preserve some dignity in defeat. They had fought a superior enemy with inferior tools, and the outcome had been predetermined by factors beyond their control. The cavity magnetron, that small device developed in a British university laboratory, amplified Allied technological advantage into strategic victory. It was not the only factor, but it was a necessary factor, the specific innovation, that enabled effective anti-submarine warfare just when the Battle of the Atlantic hung in balance. And for that reason, it deserves recognition as one of the most significant technological developments of the Second World War, even though few people know its story or understand its impact. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.